Um, Good afternoon or good morning, everyone. I'm here to talk about the global one-dimensional Earth model, and this is group 4. My name is Okaimano Obunna. So, to start with, what is scientific modeling? Scientific modeling is the scientific activity in which scientific activity aim at which to make a particular part or a feature of the world easier to understand, easier to define, evaluate, and ascertain, so to say. So, having said that, one-dimensional models are all based on equilibrium method, in which a slab of a deformation of material can be isolated. So, let me take you down to the few things you should learn or you get yourself acquainted this morning. I'll give you the introduction. I'll also talk about the preliminary reference Earth model. We call it PREM. We'll also talk about the IASP 91 velocity model, and lastly I'll talk about the model IAK 135, and the updated version of it. So before you get yourself acquainted with those models and how are they being used, so you need to understand the internal structure of the Earth, the crust, the mantle, the core, and the inner core and the outer core. So you need to get yourself acquainted with those compositional structure of the internal structure of the Earth. So, having said that, the in-depth knowledge of the tama and the compositional structure of the mantle is a fundamental for understanding the Earth's internal dynamics. So, to a very first approximation, the Earth is made up of a concentric spherical shapes. We all know that, and the internal structure of the Earth can be described in terms of variation of the properties as a functions only of depth. So, one different one-dimensional reference seismological Earth model has been constructed, and we should know that constructing a reference model requires some choices. The choice like types of the data, to be used, the computational ease, and the goal of the model. And we also know that the different types of the reference model does not represent the Earth structure in the same way. They have their own way of representation. So the PREM has their own way of representation when you use it. The IAK 135 and the IASP 91. So we also should know that models are calculated from different data sets and frequency, and may be represented in different mathematical ways. Yes. So also, models relying on body waves are often inherently biased towards structure beneath the continent, and basically that is a little bit upper mantle and the lower, just upper mantle, I think so. The P waves a bit biased, when I was talking about all those things, so you get yourself acquainted with what I'm talking about now. I'm just giving you the preamble of that. So, having said that, reference model is a reference model is an approximation of the real Earth. They are used for the following purpose: identification of the location of the earthquake, which usually involve conversion of times to distance, and require you of having the knowledge of the wave propagation of the velocity. And also it helps us in identifying different kind of seismic wave from seismic record, and this is guided by calculation of the predicted time travel, and also it helps us to predict the real path, which require you to have the knowledge of the velocity structures and it also helps us to for modeling of the propagation of wave from the earthquake, and this also requires you to have knowledge of the velocity structure. Talking about velocity structure, you will see it in a bit. Okay, so here is this structure or internal structure of the earth. Like I say, you need to have a knowledge of these structures. Not that the modeling is not done in a external structure of the earth, but my emphasis lie heavily on the internal structure of the earth. This is below Sia, which is the continental type crust, and here we have the mantle, we have the lower mantle, upper mantle, lower mantle, the outer core, the inner core. So the thick line actually mark the discontinuity due to the phase changes or compositional changes, right? You can see even is used a color to differentiate it with some components in it and minerals. So here is the velocity structures. You can see the dotted line is the is the X wave, and the thick line here is the P waves, and this is the density. We have also the attenuation structures, which involve in most of these structures. And let me put this that almost all the layers, like all the layers have their velocity structures. Some have the density structure, yeah, and the attenuation structures. Now, talking about the P wave and S wave, let me just lay more emphasis on it, because I'll also be using it very well in this presentation. So like I say, this is the corresponding depth dependent velocity structure for pressure wave and the secondary wave. Yeah, P waves, we all know, is one of the two types of the elastic body waves called seismic wave from seismology. P waves travel faster than any other seismic waves, and for this reason they are the first signal from earthquake to arrive at affected location and the location or seismography. P waves travel through all kind of medium, both solid, liquid, and gaseous, unlike the S waves that do not travel through liquid medium. Now, talking about the S wave is also one of the two main types of the elastic body waves, and they travel through, they propagate through a body of an object. They do not travel through a liquid medium. But P waves are transverse in the sense that the oscillation of the S waves or S wave particles are perpendicular to the direction of the wave propagation. Yes, so S wave do not travel through this modern outer core. They do not propagate through this outer modern core. Yeah, reason be that they cause shadow zones to S wave opposite to their direction. So, but they can propagate through this inner core, solid inner core here, with the help of the P waves. So when P waves strike the modern outer core here, at the oblique angle, they produce S waves, which propagates through the solid medium of this. When this S wave, which are formed after P wave strike this boundary, so S wave also strike the boundary at the same point and at the same angle, oblique angle, and in turn they produce P wave, which will propagate through the liquid medium. So this whole analysis actually helped the seismologist to get acquainted and the knowledge of the physical property of the inner core here. So yeah, so let's go to the next one here, which is the first model we'll be talking about, which is the preliminary reference Earth model. Yeah, for many years now, the most widely used reference model on seismic velocity in the Earth has been preliminary reference Earth model. This model was produced by Adam Zwanke and Addison in 1981 in response to the guidelines of the Standard Earth Model Committee of International Association of geodesy, and the International Station of Seismology and Physics of the Earth interior. So this whole model was produced or constructed to fit a variety of different data sets, including the oscillation center frequency measurements, surface wave dispersion observation, travel time data for number of body waves phases, and basic astronomical data. Like I said before, it is a one-dimensional model and it represents average Earth properties. Talking about the property, including the elastic properties, the attenuation properties, density, pressure, and gravity as a function of planetary radius. Having said that, PREM or preliminary reference Earth model is being used as a purpose for seismic topography. Yes, so seismic topography is a technique used for imaging subsurface of the Earth with seismic waves caused by earthquake or explosions. S wave, P waves, and surface wave are used majorly for the topographic model of a different resolution based on seismic wavelength. So having said that, it actually incorporates inelastic dispersion and anisotropy, and therefore it is a frequency dependent and transversely isotropic for the mostly upper mantle. Yeah, you can also get it in a lower mantle of the internal structure of the Earth. So having said that, PREM is based on the measurement of the normal mode engine frequency, about 1000 modes, summary tells seismic body travel times, about 500 summary observation, individual P and S tells seismic travel time observation, and normal mode attenuation measurement, mass and moment of inertia of the Earth. Right? So it's also the data we are inverted to retrieve P waves, S wave, density, Bank alteration. This is Bank alteration, and this is the shear alteration as a function of depth. Right? So having said that, the model was actually designed to valid for reference period of 1 second, but was also tabulated for 200 seconds. So knowing the alteration structures, the correction for computational of a different resolution or different a different period of a reference period of time can be calculated, right? So PREM is giving us a table giving a value of the P waves, S wave, attenuations, Bank attenuation, and the shear attenuations, right? What that is vertically and horizontally polarized waves respectively, both the S wave and the P waves. Sorry. And there is also a parameterized version of the preliminary reference Earth model, allowing the accurate interpolation of the seismic waves. So this is the effect of the anisotropy of the seismic wave passing through when shear waves or when seismic wave propagates through anisotropic medium. There's a split of the shear waves into a slow red component and a fast blue component. Yeah, this is basically the effect of the anisotropic media. Seismic wave speed depend on wave propagation direction and polarization. Unlike this one, it is transversely anisotropic media. Seismic wave travel at different velocity depending on the polarization and propagation. You can see that here the direction of propagation is actually in a vertical motion, this arrow here, and here it is horizontally. So this is just the effect of the anisotropic media transversely, yes. So and Prem is, so to say, that Prem has traversed isotropic in the upper mountain. So there is a thing we need to draw, a conclusion we need to draw in this preliminary reference Earth model. There is an artificial discontinuity which actually give it an upper edge to other reference model. In other reference model, the discontinuity usually occur at 410 kilometer to 660 kilometer, but this the discontinuity occur at 220 kilometer, and this is from zero down to this place, you know, continental the crust has a 35 kilometer thick, which is up here a little bit here. So but in the upper mountain, the discontinuity of the preliminary reference Earth model is at the 220 kilometer. That is even before this 500 kilometer here. That is almost here, half of this place, right? But other reference model, the discontinuity actually occur at 410 to 660 kilometer. So that is the depth of the transition zones of discontinuity. So transition zone occur at 220 kilometer in this model, and that is the major drawback in this model. You can see the velocity structure of the P waves and the S wave here. You can see that this is the horizontal P waves of polarized waves, and this is the vertical of the polarized wave of the P waves. And also occur here, this is the vertical of the S wave. We know that S wave is a secondary wave, or you call it a shear wave, and this is the compressional wave, or you call it a pressure wave or P wave. So this is the density structures, and this is the attenuation structures. And yes, there is also a 3 kilometer thick layer of water in these layers. We should draw that this whole thing is just the velocity, density, and the attenuation structure of the preliminary reference Earth model on an isotropic form of preliminary reference Earth model. Good. So let's go to the second model. We'll be talking about the IASP91 velocity model. This model was produced by some commission on earthquake algorithm of the International Station of the Seismology and Physics of the Earth Interior. So it's basically meant to fit in or built to fit in one frequency data and locate earthquake in some cases. Like I told you, that is the major reason of one-dimensional reference Earth model, is to locate the earthquake and you know, get the positions. So having said that, the crust is chosen to be the representative of the continent. We all know that, and because that is where the seismometers or the reporting station are being located. So this model is the major, also the reason why it is made is to predict the seismic waves or travel times, and for that reason the crustal layer is about 35 kilometer thick, and 35 kilometer thick of and different and it's divided into two sorry, let me get that correct. Crustal layer is 35 kilometer thick, split into two layers, yes, of discontinuity about 10 kilometer depth. And it does not include the water layer, and mostly there is no it does not resolve the density, and it does not resolve attenuation. This model does not resolve attenuation too, and there is exclusion of the water layers, so unlike the previous ones I talked about. So it's also need to draw that The mountain discontinuity, like I told you, that it is set at 410 kilometer and 660 kilometer. Like the other one, the artificial of its discontinuity is about 220 kilometer. And also in the lowermost mountain there is a gradient change at 2740 kilometer depth into the D layers. D layer is just a lower bit down to of the mountain, the lowest most mountain of the internal structure of the earth, like a bit crack line, like in a zigzag form. That's called a D layers on the internal structure of the earth. So there is a gradient change in that layers in this, using this in this model. And also in the internal and the outer core radial were set using a normal mode inversion, and the core velocity structure was also taken from the preliminary reference earth model. So basically velocity are parameterized as a various as a linear, quadratic and cubic polynomial, and different phases are reduced to their real parameters, which make computation simpler for us. So having said that, due to the high frequency of the p waves in this model, in this context, the p wave travel time are easier to measure due to the clearer time windows in which they travel, right, in which they arrive. And for that reason, the p wave structure is said to be better, resolved than the s wave structures, right? For that, because of the high frequency and because of the travel time, which is easier to measure. So having said that, the upper mountain velocity are likely more a bit biased. Like I mentioned, that some body waves are inherently biased, so upper mountain velocity are likely a bit biased based on even source and receiver location than the lower mountain. So we also should note that the model was verified using test events, a collection of the nuclear explosion and earthquake, for which the location and the origin time were precisely known. Yes. So the bias average of the wave used to define the velocity in this region are strongly affected by the large lateral variation in seismic wave speed at the top of the mountain, and that is also why that upper mountain were a bit biased, by the uneven source and receiver location. So yeah, sorry. So the okay. Yeah, this is the structure of the IASP91 velocity model. So you can see here that the p wave structures, so okay, start from here down to D here. This is p wave structure, and there is no vertical and polarized waves in this velocity structures. So also you need to notice that there is no density. It does not resolve density and does not resolve attenuation, and you can see the structure is not here. And also there is no water layers. Normally the discontinuity at the mountain is at the 400 to 660 kilometer depth. So also notice the structure of all these velocity of internal structure of the earth, that they are not representing in the same way. Like I actually explained earlier, that they have their own different way of representing the internal structure of the earth. So not in the same way, both the p wave and the s wave. So you notice that too. So the last one I'll be talking about here is the AK135 model. and the updated version of it is AK135 F model. So this model was actually refined to, represent, sorry, let me get that correct. It was refined, it was built to refine the other model I talk about, which is the IA SP91 model. So that one, there was no inclusion, they did not resolve attenuation and density. So this one was actually built to refine that model. And ISC travel time, to improve the travel time accuracy and increase the fit to core faces. Yes, so the inverted include normal mode data to constrain attenuation and the density. Exactly. So that, but it is only for the updated version, which is this one, because here this particular model does not resolve the attenuation and it does not resolve the density, but the updated version does that. So the AK135 is distributed as a spherical average and continental mode, right? So attenuation structure is introduced to obtain agreement between the high frequency body wave data and the normal mode. So having said that, the upper mantle is about 1000 kilometers of the outer core, upper 1000 kilometers of the outer core velocity structure, which is only for P wave because the S wave does not propagate through a medium, had previously been poorly resolved, as the rare part of the PKP branches use sample deeper into the core. In this model, previously unused branches of PKP were included, which is the PKP AP, AB and PKP BC, right? So the certain phases were excluded from the inversion, which is the direct P wave and S wave at distance 25 degree, that is less than 25 degree. There were a bit not included, and that are known to be strongly affected by the upper mantle. So the P waves and the S wave at a distance of 25 degree, that is less than 25 degree, we know that it is strongly affected by uppermost heterogeneous mantle structure. So it's a bit excluded from this model, and the P and S wave coda phases, of which the onset time are more difficult to pick. So these two features were excluded or were removed from this because of the effects, the effects and the difficult to pick the coda phases. So having said that, as you can see here, okay, this one, I think I forgot to say something here. The crustal layer is also chosen here to be the representative of the continents due to the reporting station located there. So in updated version of the AK135, the crust is chosen to be 18, but in AK135 is chosen to be 35, right? So in also the IA SP91 model is also chosen to be 35, but in this case it is chosen to be 18 with additional 3 kilometer water layers. So this is where, and this is how the water layer comes into play in this model, because normally it is not it does not include it, but because of the chosen layer of the crustal, which is about 18 kilometer up a bit, the 3 kilometer depth were added to include the water layer with this model. So I'm also I stand to be corrected in much of the what I'm saying. Yeah. So yeah. So the next one here is the, okay, that is the structure of the updated version of the AK135 velocity model. Here you can see the model from 0 down to the 60,000 kilometer depth. So we know that from this 0 here is from the where we are living, this is the continent, this is the oceanic, and the Sima and the Sia. So down to this where you can even find the nickel, which is the inner core of the internal structure of the earth. So this whole thing is the P waves, and this one is the S wave. Take a note that they are not representing the structure of the earth in the same manner or in the same way. So you can see here there is the resolved density and attenuations. You can see this is the bulk attenuation and this is the shear attenuations. So this is basically the velocity structure of the updated version of the AK135 velocity model. So having said that, so this is the summary of the common reference model. You can see, like I said, the under PREM, people that produce it is Wanke and Addison in 1981, and also is Kenneth and Egda, and same Kenneth and Kenneth work with this one too, and updated version of it. So the period is with attenuation correction for 200 seconds, but the normal one is the 1 second. This is 1 second and this is 1 second. That is the period of their time. So water layer, yes, 3 kilometers thick. Like I said, it does not include water layers, and this also, yes, 3 kilometers thick. Resolve parameters is preliminary reference estimate resolve P waves, S wave, attenuation and density. And you can see here they do not resolve density and the attenuation. So they do here only on the updated version, which I stated here in this only. So in the AK135 they do not resolve attenuation and density, but updated version they do that. So here features the upper mantle discontinuity at 220, which is the artificial discontinuity I talked about, is the gradient change. So here P model, P waves better resolve than S wave in this model, which is IASP91, and here outer core well resolved by APK, PKP, differential travel time, density and alteration also better resolved. So anisotropic and isotropic. In preliminary reference Earth model, is transversely anisotropic of 2 to about 4% from 80 to 220 kilometer depth. So in this one is isotropic and this is isotropic, and like I told you that the S waves, they are transverse in the sense that the oscillation of the propagation of the S wave particle are perpendicular to the propagation direction. So this is the whole mantle, and this is the structure of it. Now take a look at this. This is the different model I talked about, the AK135, the updated version, and the IASP91 and the PREM. So you can see that there's a deviation, not that they are represented. The red one is the PREM. You can see it's not on the same line. There's a deviation. So that also gives the correction of what I'm saying, that it does not represent in the same manner. So the same thing with the S waves and density. So this is the attenuation, both the bulk and shear attenuation. You can see they are not giving us the same structures. So here is the upper mantle, is the velocity structures here, P wave and S wave, is not still the green line is the IASP9 one. You can see is a bit, the deviation is a bit clearer here, and the PREM, which is another model used, it's not the same manner. So take a look at all of them. You can see that the representation of the structure is not in the same way like I iterated earlier. So this is the lower mantle and this is the inner core of this. You can see the inner core, the P waves here, it is different. It's actually not in the same line. So not in the same line. So this whole thing is a comparison of the common reference model, P waves, S wave, velocity, density, bulk, and shear attenuation, right? Structures. And the attenuation scale is truncated as shear attenuations. Shear attenuation is extremely low. So yeah, the limitation, it should be stressed that one dimensional reference model are zeroth order of approximation of the Earth. In order to compute travel time of seismic waves and compare them to review data, correction due to Earth, ellipticity that depend on the phase used need to be applied. So the model often most poorly represent the uppermost and the lowermost mantle. Yeah. So and then the construction of these various model, the author are often explicit in stating the limitation of their production. So there was no a bit there's a need to have a better structure that will resolve the uppermost and the lowermost mantle for the models. So there is a deviation and it does not give the better presentation of the uppermost and the lowermost mantle, even the inner and the outer core. So we we stress that model AK135 is designed to represent the smoother empirical travel time, and so should be very suitable for predicting the arrival time of the wide variety of seismic phases for use in event location or phase association procedure. So we have to be cautious about direct interpretation of AK135 as a full presentation of the seismic velocity in the Earth, right? And it should be stressed that such a velocity model is intended as summary of seismic travel time, and because of the uneven graphic distribution of the ray path sample by the event in the IIC catalog, we represent no simple average of the Earth. So this is the conclusion. Like I said, the reference model, the three reference model I talked about, is the all one-dimensional reference model, and they represent the Earth property, which is the elastic properties, the attenuation properties, the density properties. They also include the P wave and S waves, and it is a one-dimensional reference model, yes, and is a the model are very good approximation of the Earth structures. So that is the little way I understand the different types of the model given to me to explain. Thank you very much, and remain blessed.